Right, during this chapter, we want to introduce the Schrodinger equation and the derivation of that equation. It's really one of the most important things that's happened in physics in the last probably 150 years or so. So we'll spend some time talking about this. First of all, we want to talk about when quantum mechanics is necessary rather than just using classical mechanics, things developed by Isaac Newton and so on. And the two main criteria are going to be the magnitude of that de Broglie wavelength we talked about in the previous chapter. When it is on the order of magnitude of the size of the problem, then quantum mechanics becomes a viable option to do calculations. It becomes necessary. The other thing is the degree to which the allowed energy values form a continuous energy spectrum. When the energy spectrum is or appears to be continuous, then quantum mechanics becomes unnecessary. But when there are discrete portions of energy and spaces between them that are large compared to the size of the problem, then quantum mechanics becomes necessary. To determine whether that continuous energy spectrum is going to be an issue or not, we'll need to do a calculation called the Boltzmann distribution. The root mean squared energy of a group of particles is going to be 3/2 kT, where k is the Boltzmann constant. It's R over Avogadro's number, and that root mean squared energy is talking about kinetic energy for a group of, say, gas atoms. And when that is the case, we can calculate the number of particles in a particular energy level that have a particular energy using this formula. Now look, it doesn't necessarily calculate the number of particles themselves, but it calculates a ratio of how many have one particular energy compared to another particular energy. And we compare the actual energy values in this area, so we could call this a delta E, or a difference in energy. There's the Boltzmann constant and temperature again, and then the G's refer to the degeneracy of the system, the number of different ways something can have the same energy. Alright, so we want to talk about, in our example, 1,000 particles that could only have two different energies allowed for them. One we'll call energy 1 and one we'll call energy 2, and they have a difference between them that's known to be 1, and we'll assume that the degeneracy of the system, the number of ways that that energy can be held, are equal to one another. And so what we want to do in our example is graph the number of particles. I want you to try this one on your own, N1 and N2, that are in those states as a function of kT over difference in energy. And then explain your result and talk about at what value, calculate what value do 3/4 of the particles have E1, where only 1/4 will have E2. And that should all be able to be doable on a graph. So try that out with Excel on your own, and we'll look at the results in class the next time that we meet. Now, if we want to start thinking of problems in terms of quantum mechanics, that means representing the things that we want to calculate, the systems we want to calculate, as waves. So a wave can be represented pictorially by wave fronts corresponding to the amplitude, maxima, and minima. So for example, instead of thinking of this as a wave, we can say that each circle, if this is a dot point of light, represents a wave front, a maximum or a minimum for that wave, and so they would each be a certain wavelength apart. And so yeah, a point source of light would emit these spheres of light. Light passing through a slit can be represented as cylindrical waves. If we have plane light coming toward this slit, as it passes through the slit, it will spread out in cylinders. Now, if you take a look at this situation here, there's going to be a pretty good curvature per square meter, say, to this sphere. Less for this sphere, less for this sphere. When we walk around on the Earth, it gets the appearance of being fairly flat, and that's because it's a very, very large sphere. So the larger the sphere is, the less curvature you have for square meter. So spherical waves that are sent from far, far away, say light waves that come here from the sun, have the appearance to a small system of being plane waves. Now, the amplitude of a wave can be described by a wave function. If we consider the waves of constant wavelength and constant frequency, where frequency is 1 over tau, where tau is the amount of time it takes a wave to pass, and the velocity of the waves then would be wavelength times frequency, and we're talking generally here, not just light waves, but the velocity would be c in this case if we're talking about light waves, and it would be less than that for sound waves. And the peak to peak amplitude we're going to call 2a, the distance from then the equilibrium point up to the top of a peak or the bottom of a valley. So then we can write this wave function where we say that the wave function is equal to a, that amplitude we just described, times the sine of 2 pi times x, how far we are along the x-axis, over wavelength, minus t, the amount of time that has passed, over tau. The wave function then is going to be 0. We're going to be at the equilibrium point for any place where 2 pi times this equals n pi. Or we could rearrange that and solve for x. Anytime x equals the wavelength times this, will be at a 0 point. And as t increases, as time goes by, x increases as well. So we can rewrite that wave function a little bit simpler terms where we say k, lowercase k, is 2 pi over the wavelength. We call that the wave vector. And omega is 2 pi times the frequency, and we'll call that the angular frequency. And so kx minus omega t is the phase of the wave function. So we've just defined several wave function terms. This wave function is beginning at a point in the origin, with an equilibrium point at the origin. If we want to shift the wave function to the right or the left and have it begin from a different spot, then we would add an additional term inside of the sine to cause that shift to the right or to the left. Now let's think about two waves that are moving in opposite directions with the same frequency and the same wavelength. The total wave function would be a times the addition of those wave functions, where since they're moving in opposite directions they have opposite signs on the omega t. We can use a trig identity. I don't expect you to memorize these trig identities, but they'll be given to you on a test if you have need of them. But we can use this trig identity to replace this term with this one, and now we have resolved this problem where we say that the wave function is a separated wave function that has one term multiplied by another. The one term depends only on x and not on time. The other term depends only on time and not on x. So this function is the product of two wave functions that each only depend on one of those variables. So the nodes depend on x without moving, and so we call this a standing wave. So we can generate a standing wave. A pictorial representation of a standing wave would be a jump rope, and you can do we can shake our hands a little bit as we twist a jump rope to make nodes appear at different points in the jump rope, but that would be an example of a standing wave whose wave function would be described this way. Alright, now here's another example, a classical non-dispersive wave function for waves that travel in a medium for which all frequencies travel at the same velocity. So light would be an example of that. The second derivative with respect to x of that total wave function is 1 over the velocity squared times the second derivative with respect to time. What I'd like you to do is demonstrate algebraically, try this on your own, and we'll work it out together in class, that the traveling wave function that we've just described is a solution to that problem. In other words, show that if we take the second derivative of x, second derivative with respect to x of this function, that we will get 1 over square velocity times the second derivative with respect to t. And we'll do that one in class together as well. Now, one other thing that comes up quite a bit in quantum mechanics is this idea of complex numbers or complex functions, and that's because these two functions that we've written are algebraically equivalent. We put in an additional phase factor to correct for the fact that the cosine is a half a pi off on the x-axis from where the sine is, and then we can put in a new variable to take care of this phase shift variable, and use Euler's formula to rewrite this wave function as a exponential function. But when we do that, we introduce complex numbers. We introduce the square root of -1 into the problem. When we write RE here, that tells us that we're only using the real part of Euler's formula. We're ignoring the sine term when we convert from cosine to the exponential, but still it generates the square root of -1, the I term in that function. And so what we'll need to do, and I want you to try these on your own, go ahead and pause. What we'll do here is when convenient, we'll write the wave function in that fashion, and that's going to cause us to want to do a little bit of practice with complex numbers. A complex number or function can be written in the form a plus ib, where a and b are real numbers and I is the square root of -1, or those numbers can be rewritten as r times exponential I theta, where r is the square root of a squared plus b squared from up here, and theta is the inverse sine of b over r. And so we can convert one to the other in those areas. The complex conjugate of a number is found by substituting -I for I anywhere in the number. And so whenever we're going to square a complex function, what we're saying is we're going to multiply that function by its complex conjugate. We'll call that the square root of that the absolute value. And that's also equivalent to the R term that we just defined. So like I said, in a few seconds, go ahead and pause the video, and we're going to work these practice problems in class together next time we meet. And just get some practice in solving these problems, determining the magnitude of several different complex numbers, as well as converting from one form of complex number to the other. And so try these out, pen and paper on your own as you get a chance, and we'll work them together in class tomorrow, or next time we meet.